This is video 4. We present here the definitions and notations of path assemblies. Along this video, we will use the following tile set T to build our examples. This is the tile set introduced at the end of video 3. Also, we will use this tile assembly system. The seed is represented in black. This is the directed tile assembly system introduced at the end of video 3. We consider the grid graph. We present here another formalization of an assembly. This formalization will ease the analyze of a tiling assembly system. Let's put some tiles on the grid. Here we have represented some tiles on the grid. A single tile is encoded as a couple made of a position of the grid and a tile type. For example, consider that the dotted position is the origin of the grid graph. In other words, the position of coordinates 0, 0. The tile in gray is represented by the position of coordinates -4, 2 and the tile type T23. Now all the tiles on the grid are represented as a sequence of tiles P. In this example, the tile in gray receives the index 2 and is named P2. The sequence of tiles is of length 14. The domain of a sequence of tiles P is the set of positions occupied by a tile of P. We represent here the domain of the previous sequence of tiles. The underlying path of a sequence of tiles P is a sequence of positions such that for I from 1 to the length of P, the position with index I is equal to the position of the tile Pi. Note that we will always consider cases where the underlying path of a sequence of tiles is a path. Concerning the notation, sequences of tiles are written as overline P whereas paths are written with only the letter P. If we use the notations overline P and P, then overline P is always a sequence of tiles and P is always its underlying path. During our explanations, we do not precise the overline, but when necessary, we precise that we either consider the sequence of tiles P or its underlying path P to avoid ambiguities. Note that a sequence of tiles can contain several tiles at the same position. In this case, its underlying path is not simple. We say that a sequence of tiles is consistent if and only if all tiles which are at the same position are also of the same type. In our example, the sequence of tiles P is consistent since a position is occupied by at most one tile. A consistent sequence of tiles P can also be represented by a partial function alpha such that P and alpha have the same domain. This partial function alpha is called the partial function associated to P. In our example, the figure represents the partial function alpha associated to the previous example is drawn. Note that the labels of the tiles and all the interactions are drawn. In our example, alpha is an assembly. Finally, a sequence of tiles P is a path assembly if and only if four conditions are met. First, P is consistent and thus the partial function alpha associated to P can be defined. Secondly, the partial function alpha is an assembly. Thirdly, the underlying path of P is a path. Fourthly, the underlying path of P is a subgraph of the binding graph of alpha. Almost all the sequence of tiles considered along the proof are path assemblies. Except for some few times where the sequence of tiles is inconsistent, we will meet no other cases. From now on, to represent a path assembly, we will draw the tiles, the underlying path of the path assembly and the label of the first and last tiles. Path assemblies have the following advantage on assemblies. Consider only the tile P1. This single tile is an assembly. Since P1 and P2 interact on their common side, the tile P2 can be attached to the tile P1 to obtain a new assembly. Now, the tile P3 can be attached to the tile P2. The tile P4 can be attached to the tile P3. The tile P5 can be attached to the tile P4. The tile P6 can be attached to tile P5. The tile P7 can be attached to the tile P6. The tile P8 can be attached to the tile P7. The tile P9 can be attached to the tile P8. The tile P10 can be attached to the tile P9. The tile P11 can be attached to the tile P10. The tile P12 can be attached to the tile P11. The tile P13 can be attached to the tile P12. And we finally obtain the path assembly P. Then, unlike assembly, a path assembly also encodes the way to produce it from a single tile. Now, we say that a sequence of tiles is simple if and only if each position is occupied by at most one tile of the sequence. In our example, the path assembly P is simple. Note that, if the sequence of tiles P is simple, then its underlying path is also simple. Now, we focus on the interactions between a path assembly and the seed. First, a path assembly is consistent with the seed if and only if the seed is consistent with the assembly induced by P. In our example, the only position which belongs to the domain of P into the domain of the seed sigma is denoted as a black tile with a white dot. This tile is P1. The type of P1 is T22 and its position is -32. Now, sigma of -32 is equal to T22. Then the path assembly P and the seed are consistent in our example. Now, if the path assembly P and the seed sigma are consistent, then abusively we denote by P union sigma the partial function which is the union of the assembly induced by P and the seed. We represent here the union of P and sigma. Finally, we say that the path assembly P is producible by the tile assembly system if and only if P union sigma is defined and is an assembly. In other words, if P union sigma is producible from the seed. Along the proof, we consider path assemblies which either does not intersect with the seed or share only one vertices in common with the seed. This vertex is P1. The video 7 shows that these hypotheses can be done without losing any generality. Now, we say that the path assembly P grows at distance lambda of the seed if there exists a position U in the domain of P such that for any position V in the domain of the seed the distance between U and V is at least lambda. For our path assembly P we use the same notations than the ones introduced for assembly and graph. For example, lowercase xp represent the lowest abscess of a position occupied by a tile of P. Also, the direction of the path assembly P is the direction of its underlying path. In other words, it is the vector starting at the position of the first tile of P and ending at the position of the last tile of P. The direction of a path assembly can be switched. Here, we represent the path assembly P' obtained by switching the direction of P. A path assembly can be translated by a vector V. In this case, all of its tiles are translated by V. When a tile is translated, only its position is modified, its tile type is not modified. In this example, we represent the path assembly P second obtained by translating P' by V', where V' is the direction of P'. When we consider several path assemblies, we may try to fuse them into a big one. For the same reason explained in video 2, we will not make the union of two path assemblies, but we will rather concatenate them. Here we represent the two path assemblies P' and P second. The last tile of P' occupies the same position as the first tile of P second. Nevertheless, the tile type of P' 14 is T26 and the tile type of P second 1 is T22. These two path assemblies are inconsistent. In this case, we cannot define their concatenation. Let's go back to the path assembly P. We will come back to the concatenation soon. Now a segment of a path assembly P is a subsequence of P. For example, we represent here in gray the tiles from P3 to P12. Let's remove the other tiles. We obtain a subsequence of P denoted by P312. This subsequence is called a segment of P. In our example, we represent this segment by the path assembly Q of size 10. Now, we say that a path assembly is a candidate if and only if the tile type of its first tile is the same as the tile type of its last tile. In our examples, the path assembly Q is a candidate segment of P, whereas P is not a candidate. We represent here the path assembly Q' obtained by translating Q by W, where W is the direction of Q. Now consider the interactions between Q and Q'. The last tile of Q occupies the same position as the first tile of Q', but in this case, both of these tiles are of type T24. In this case, we can concatenate Q and Q'. Here we represent a path assembly R, which is the concatenation of Q and Q'. The size of R is 19. Thus the concatenation of two path assemblies requires several conditions. First, the last tile of Q must be the same as the first tile of Q'. In this case, the concatenation of Q and Q' is correctly defined and produces a sequence of tile R. This sequence of tile R is a path assembly if and only if Q and Q' are consistent. Indeed, there may exist other interactions between Q and Q' which can create inconsistency. A candidate path assembly can be extended into a B-infinite sequence of tiles. Here we represent the extension of Q, which is a B-infinite path assembly called omega Q. The extension of a candidate path is always correctly defined, but it is a path assembly if and only if it is consistent. The four other extensions of a path assembly are defined similarly to what has been done in video 2 on paths. A simple path assembly P is good if and only if it is simple, it is a candidate and its underlying path is good. In this case, the extensions of a good path assembly are always correctly defined and are always a path assembly.